Buongiorno. My name is Dr. Maria Setti. I'm here representing Pace University, which is located in Pleasantville, New York, in the United States. My research topic today is going to be a knowledge-driven web tutoring system framework for adaptive and assessment-driven open source learning. Also contributing to this research is Dr. Lucian Tao and Ying Jing. I also like to thank IEEE and University of Torino for having us attend this conference today. First, I'd like to go over the introduction of this research, the background, the challenges, the issues, and the solution methodology. Introduction and background. In the last decade, significant research studies have been conducted on learning objects, which are self-contained learning resources with integrated learning schedule and assessment devices for a specific topic with clear, specific learning outcomes. But these studies were limited by categorizing, reusing existing learning resource. They don't have knowledge mapping to integrate these learning objects together for customized adaptive learning environments. Web and computer application-based tutoring systems started to take advantage of learning objects to automate learning process. Factors that contribute in this direction include, first, diversity in the target population participating in learning activities. Second, diversity in the access media modalities that can one effectively utilize today in order to access, manipulate, or collaborate on education content and learning activities. And lastly, diversity in the context of use of technology. However, this goal cannot be achieved at a massive scale using traditional approach. Although there are many tools and various approaches for developing learning object concepts, the objective is to first adapt to the learner's needs, second, assess learner's performance outcome, third, provide feedback recommendation, and lastly, adjust learning path and learning order accordingly. Web-based intelligent tutoring systems do not offer automatic feedback recommendation for students on which learning objects to recommend, what learning path and learning order learners should follow in order to better understand learning concept. We're going to go now into the cyber learning challenges and what those are. So cyber learning presents numerous challenges such as, first, the lack of knowledge representation. Second, the lack of integrating learning objects to support effective learning experience. Third, lack of instructor personalized guidance and feedback. And lastly, the lack of semantic knowledge assessment-based study. First, we're going to look at the lack of knowledge representation. In the past few years, Pace University has conducted research on effective knowledge representation and knowledge-driven intelligent information system. While the industry standard used web ontology language, which is also called OWL, to represent knowledge in ontology, we believe ontology is not enough or natural to represent most domain knowledge to support the is-a or inheritance relations. Emulating custom relations with object properties in OWL is cumbersome and not suitable for domain experts to encode and validate knowledge. Now we're going to take a look at the lack of instructor personalized guidance. Many e-learning environments are challenged with the delivery of how to present learning materials to their students. First, e-learning environments tend to teach learning materials in a restricted order for all learners regardless of students' learning level. Secondly, learning objects have no intelligence to guide users' learning abilities or personalize their learning materials. Thirdly, the assessment can't evaluate or recommend whether you understood the lesson or whether you should be redirected back to learning topic before going ahead to learn the next topic. And lastly, some learners are beginners while others are more advanced. How do we address some of these issues? Now we're going to take a look at the lack of instructor experience. Here I make a comparison between the traditional classroom and the online learning system, and we take a look at what the difference are between the two and how we can improve them. So in a traditional classroom, we have an instructor that is present all the time in front of the learners. Secondly, we have instructor face-to-face interaction with their learners. Thirdly, instructor can give their experience about the subject matter to their learners. Lastly, instructor can also give feedback immediately because the learners are sitting in front of the instructor. On the other hand, online learning systems, students lack the instructor experience because they're not present. Students lack the instructor feedback because they're not present. Students tend to get disoriented on learning order. And fourthly, students get disoriented where to find resources. And lastly, students lack guidance on learning path. So here I just made the comparison and what the issues are between the two. Next, we're going to take a look at the lack of assessment-based study. Most mainstream learning systems have predetermined fixed path delivery of content. Secondly, they lack agility in adapting to learners' mastery state. And lastly, they're limited in their ability to tailor learning experience to individual learners. On the other hand, we have an adaptive intelligent learning system, which needs an accurate model for the learner, needs a model of knowledge domain, needs the ability to evaluate the difference between the two models, and lastly, needs to identify or divest on demand and in real time instructional strategies that will achieve desired instructional outcomes. So here we just gave you a basic assessment on what the lack is for assessment-based study. Here we start to talk about what our solution methodology is. This research supports to improve cyber learning by implementing a knowledge-driven web tutoring system framework for adaptive and assessment-driven open source learning using the following methodology. First, we want to extend ontology using the Pace University Knowledge Graph to support custom relation. Secondly, we want to extend the OWL with minimal syntax extension to support custom relation as first-class relation. And lastly, we want to extend the Stanford University Project Protege, which is an open source IDE for visually developing OWL-based knowledge representation to support the declaration of custom relations and the mathematical properties. Next, we're going to look at the tutoring system tier architecture. Here I illustrate how that architecture looks like. I have 4 different layers. The top layer consists of the client tier, which is the front-ending face to the user or learner, and it has JSP servlets and web services that presents itself to the client. The next layer, we have the educational tier. The educational tier talks to the front tier of the client tier and also the semantic tier, giving back different types of information in the dispatcher. The third layer is the semantic tier. The semantic tier contains the Pace Jena APIs that needs to deliver the information from the educational component, the data tier to the educational component and back to the client tier. And lastly, we have the data tier, which contains the database and the knowledge graph to be able to give that information back to the front end of the client tier. Next, we want to talk about contributions in this research. This research makes contribution in the area of open source knowledge-driven online tutoring system framework that is easy to be adapted for teaching any subject based on open source learning objects. First, Pace University extension to OWL that supports knowledge graph. Secondly, a generalization of ontology used to support knowledge representation with custom relation. Thirdly, instructors can use Pace Protege IDE to visually declare custom relations and encode domain knowledge of a course in a single document. And lastly, instructors' teaching experience is encoded in knowledge graph to better to support custom learning order and learning resource recommendation. The main contribution of this research is Pace Knowledge Graph is used to better model the knowledge structure of a course as well as recommended learning paths so the tutoring system could support free knowledge navigation and the common learning patterns including specialization and generalization. Secondly, a tutoring system framework is developed so instructors without information technology background can customize the framework into a full-fledged online tutoring system on any subject with any learning object, quizzes, and recommending learning orders. Now we want to get into related work that's associated with this research. Knowledge representation. Related work from knowledge representation is the foundation of any intelligent system is how to represent knowledge in a form that a computer can understand and use. First, artificial intelligence research has adopted various knowledge representation schema, including logic-based, rule-based, and code-based. Secondly, while the current industry dominant approach is to use resource description framework, which is also called RDF, to specify statements or relations between resources and entities. Thirdly, web ontology language is used to define knowledge types or concepts and relations among the concepts. That would be abstractions of resource and entities. And lastly, ontology is the mathematical model behind OWL, which is basically a set of concepts connected by the is-a or inheritance relation. And so this is just an overview of how that knowledge is represented from related works and how we take that information and we are able to extend it to improve our research. Here I show you a little picture of how that representation looks like. Here we have a vehicle domain. The vehicle domain contains different types of vehicles. Here we have a sports vehicle on the left side that is red and has a plate number of AMB 501 and contains 4 wheels. On the right-hand side, we have a truck, which is black. The plate number is BMA 502. It also has 4 wheels. These is a relations. The problem with this is that if we want to use parts, it is very difficult to do that currently with the information that we have out there, and it's not able to do so properly. So our research helps us improve the ability of doing that in our application. Knowledge representation. Here we're going to talk about how Pace University has utilized this research and improved to extend it. Since 2014, Pace University researchers have extended OWL with minimal syntax extensions so domain experts can freely introduce custom relations with various mathematical properties in knowledge representation. The resulting ontology extended with custom relation is called the knowledge graph. Stanford University open source OWL GUI editor Protege has also been extended to support the intuitive creation of the knowledge graph. This research uses knowledge graph representation of course concepts and relations to encode course knowledge structure. So now we're going to look at the cyber learning and learning objects. The popular adoption of web technology has led to unlimited open source learning resources in various forms and types. In the past decade, the United States National Science Foundation has supported many research projects on learning objects, which are basically reusable open source course modules with integrated assessment. While there are a lot of research into learning object indexing, categorization, not much investigation has been reported on the knowledge structure of each learning object and the relations among the various learning objects. This research aims to take advantage of the learning object research and integrating them into an effective course through our intelligent tutoring system framework. Next we have here is a table. We show you the technology we use and the description of those technology for the Java semantic web technology that we've been using for this research. First we have Java Enterprise, and is a popular web technology for delivering scalable web services. Next we have Tomcat. Tomcat is a dominant open source Java web service framework based on Java servlet containers. Thirdly, we have servlets. Servlets are Java classes that receive HTTP protocol, GET POST invocations from web forms or application, conduct business calculation, compose the HTML presentation of computation results, and forwards the HTML presentation back to the web or application user. Next, we have the Java Server Pages. The Java Server Pages is an additional technology abstraction of servlets to separate web computation from presentation to simplify web application development. Together, the servlets and the Java Server Pages can invoke methods of other Java components and query databases. Next, we have Semantic Web. Semantic Web is based on modeling statements with resource description framework and modeling knowledge with ontology and the web ontology language. First, an RDF statement is in a form of subject, verb, object, triplet, and data type of the subject and object are defined in RDF schema or OWL. An OWL document is an instance of XML document, and it declares concept as classes and the connections among the concepts through the is-a or inheritance relation or object properties, each of which must be defined for a specific domain range combination. OWL is currently industry standard for representing knowledge. Next, we're going to go into the design of the Intelligent Tutoring System framework. Here, we're going to look at the foundation, the solution design, reusability of intelligent web-based tutoring system framework. Here I have knowledge representation of how that is represented in our research. We have extended OWL syntax to support customer relations, thus extending the ontology behind OWL into a much more extensive knowledge graph. The following is an example declaration of customer relation, part of an implement. Next, we have an example which declares servlets containers is part of Tomcat. And lastly, we have declarations of cookie is used to implement session ID. Next, we have here is knowledge encoded within Protege. This is the tool that we use to be able to encode our domain and relations. On the left-hand side, you can see the class hierarchy of things. This is our domain with subclasses and classes. On the right-hand side, it illustrates the graph that is created with those domain and concepts with its relations. Next, we have knowledge parsing and reasoning with PACE Protege in this research. PACE Protege is our OWL knowledge graph parser and validator. It reads an OWL or knowledge graph document, validates its content against the syntax standard, conducts necessary logic reasoning to find out implied knowledge, and expose the knowledge to other applications through public APIs. For example, when the tutoring system needs to find out an example concept web server, it would invoke Paceman's public method-driven classes, which will return an enumeration of the driven concepts, including Apache and Tomcat. So here is just an example of what happens in the parsing and reasoning within PACE Jena. Next, we have integrated assessment. To support integrated assessment for each learning object, an assessment framework has been designed and implemented. First, we use an XML dialect which has been designed for representing the quizzes and scoring policies that the instructor will create visually. Next, we have the XML version of the questions will be automatically converted to HTML at assessment time and separate the scoring component and will assess the student's answer. And lastly, the Tomcat tutoring system dispatcher will invoke PACE Jena to find the available follow-up learning objects and recommend the best one based on the student's assessment performance for the previous course module. Here we have a tutoring system architecture, and we have different types of user. We have the instructor, the student, and the administrator. Here's just an illustration of what happens in our architecture during the processing of the information. Next, I'm going to explain to you the tutoring system adoption process for the instructor. The instructor, to adopt this web-based tutoring system for a specific subject, he or she needs to complete the following step. First, they need to describe the main concepts of the course and describe various relations among the concept, and then declare the custom relations if necessary. Secondly, select suitable open source learning object resources for each concept that can be presented in the web. Each concept can have multiple alternative learning objects using different media or approaches for different student preferences. Thirdly, design assessment questions for each learning object. Learning objects integrated assessment questions could be used. And lastly, specify recommended learning order for students with different backgrounds. Next, we're going to look at the framework validation through a tutorial on web technology. Here is a sample tutorial of the concepts that are used in this research. Next, we have a knowledge graph representation of web tutorial. Here is just a graphical picture of what that information looks like from concepts and relations. Next, we show you PaceGenna tutoring system application, web application, and what that looks like. Here's a simple example of the login information that is needed to access the application. Capturing instructor editing page. Here I show you how to capture the instructor's editing page. And here is a picture of what that editing page looked like and what you can do to alter the information, change it, delete, and update the information for the learner to be able to use the most current information on the application. Next, we show you the PACE Protégé custom relation and how PACE University took the Stanford Protégé IDE, customized it so that we would be able to use it to be able to make the declaration of our custom relations. Here on the left-hand side shows you just an example of what the class hierarchy for web technology looks like at the upper left-hand pane. On the pane below, we have relations. Those relations are custom relations, which PACE University customized so that students would be able to make it easier for them to take the custom relations and associate them with the concepts that are needed. On the right-hand side, we have the same picture, but it shows you information of how you relate, the relate to for these relations to each concept. So here I'm just showing you a visual knowledge declaration with custom relations. Next, I show you capturing instructor integrated assessment. Here we capture how the instructor is able to go into the system, edit the information for quizzes or test exams for the student, save it, and be able to give that information to the student on the back end. So here is another way we can edit the information, save it, update it, and give current information to our students. Here is just a picture of the tutoring system learning orders. Here I just wanted to illustrate how the system goes through a flow of going through the login page, how the learning order gets navigated through the menu for both beginner and intermediate. Next, we have the validating tutoring system effectiveness. Here is a section where we conduct the initial validation of effectiveness of the resulting tutoring system for students to learn sample subjects of web technology. Here in this experiment, we have students who participated from Fairfield University. There were 32 second-year undergrad students from the School of Engineering who volunteered to evaluate the effectiveness of the web technology online tutoring system. Among them, 4 students are from the Bachelor of Science and Technology program, 7 from the Bachelor of Science and Computer Science program, 8 from the Bachelor of Science and Computer Engineering program, and 13 from the Bachelor of Science in Software Engineering program. These students are divided into 2 groups, each having roughly the same number of students for each of the 4 programs. In Table 1, we just described how the students' volunteers are partitioned into the 2 groups. Here is the table that shows the major concentrations and the number of students for the pre-quiz, the number of students for paper quiz, and the number of students for web-based quiz. Next, we have pre-quiz assessment. All participants were required to take a pre-quiz exam on paper or through the tutoring system prior to starting the classroom. Here I have an assessment performance comparison. In this chart, I show comparison between paper quiz and web-based quizzes. Here we have students from 1 through 16 who took the paper quiz and web quiz for this research. On the left-hand side, I show you what the scores are of the quizzes. In red, it shows that that is the paper quiz exams, and in the lime green color, those are the web-based quiz exams that student took. On average, out of the 16 students for each, the average was 6.125 for paper quiz and 71.875 for web-based quizzes. This is the last slide and talks about future work for this research. In this area of study can be extended for many opportunities in the area of analyzing personalized learning with different types of semantic web languages and technology, such as first, analyzing different types of teaching strategy, second, analyzing different types of performance strategy, thirdly, analyzing different types of semantic architecture framework, technologies, tools, different types of inference logic, and application programming interface. And lastly, extend the knowledge graph to support and improve effective design and development for Internet of Things and cloud-based system. Here are our references. Thank you very much.